You guys did at least see the images of the black hole, right?
Oh, yeah.
And I was thinking about putting a post. There was a guy, like a few days before that picture came out, he was explaining the theoretical physics behind what the image should look like. And when the image came out, it's like, well, holy shit. I remember when black holes were like unicorns. When I was a little kid, we were like, black holes don't really work. It's just the math equations doing weird things. It's like dividing by zero. Right? And now we have theory about what it should look like based on the properties we predicted for black holes, and then the picture's basically, hey, I look like you thought I would. It's really cool. And the one that's the good picture that most people have seen is from this galaxy that's a crazy many light years away. The one at the center of our galaxy, we got a picture of it, but it's not nearly as good because it's not nearly as big. And there's a whole video about the size that we're talking about of these things. There's a black hole at the center of our galaxy, right?
Yeah.
If you didn't, I'm sorry if that's going to make you stay up at night. It's really, really far away. I mean, really far away, right? Huh? It's smaller than the one that's unbelievably ginormous, so it's still big. And if it was near us, we would have weird things happening. But anyway, sorry. I just want to make sure you guys, someday I'll actually be able to sit down. I haven't even been able to look at a lot of it's really cool. The whole story about how they had to use these things from all over the world, all these antennas and telescopes and radio. I don't even know exactly what the hell they used, but all over the world they had to kind of come together and make this a virtual giant satellite dish in a way, right? Just to be able to kind of get good resolution on this thing. All right, I'll stop.
Wait, so are they like big? Like bigger than like what is that, like the size of the sun or like the whole solar system?
Dude. Wow. Well, I'll if I remember, I'll send out the link to that video. There's a video that talks about what this black hole should look like, but then there's another video that gives an idea about size. So they go Earth, Sun, other suns, other suns, other suns, and then like black hole. Yeah, it's nifty. Yes.
The picture was a shadow, right? Of the shadow of the black hole?
No, it's the actual black hole itself kind of makes sense that you can't really get a picture of the black hole, but the really interesting thing is the physics behind why we're even able to see something in that vicinity, because everybody knows black hole is such that even light can't escape once it gets past a certain distance from the hole itself. But there's a lot of kick-ass cool physics about particles getting excited near it and emitting radiation. That's what we see. Anyway, there's so much cool. So we are living in a really, that piece of news makes some other shit a little bit easier to deal with that we're living in an age of. But you're living in an age where we actually have visual proof of something that we haven't had visual proof of ever before.
The wound that was around it was from stones that were wounded, not from radiation.
There's an accretion disk. There's matter that's around it that's feeding it. So what that light that's emitted is because the particles get excited when you accelerate particles, they emit all kinds of radiation in all different wavelengths. So that's why we're able to see any light, because it was far enough away from the black hole to escape its attraction. And I'm not going to turn this into black hole physics class, yeah. But I mean, there's a lot of math that went into that. There's a really nifty story about the girl, I think she's like 29 or 30 or something, the one who actually created the computer algorithm that puts together all the data to get the image created. So there's a lot to the story that's really neat. There's a lot of math, there's a lot of statistics, there's a lot of just cool visual stuff. Anyway, all right.
Tiffany Hawking died like just a year before we actually got pictures of the black hole.
What's that? Yeah, she gave a TED talk about how to get a picture of a black hole created like a couple years before now. So it's kind of cool to see her. She gave that talk, and then here she is like, see, I told you. Okay. Oh, so let's do this. So here's real quick overview. We got this guy. We got this guy. I'm leaving some space here. So I like to do these two because they both use the Z distribution. The Z-score form the normal distribution, standard normal. And then we learned last time about what happens when I don't know this. What happens if I don't know the standard deviation of the population? So what happens if I don't know that? I've got to use the best guess I've got, which would be S. And we talked about the fact that if there's something I don't know that's going into this equation, what should happen to me? It should have to make my interval wider to catch more shit, so I'm still whatever level confidence I want to be. So this new score should always be a little bigger than the Z, and that's called a t-score. So tied into this, how to use the t-score chart, is the idea of degrees of freedom. It actually came up earlier this semester, dividing by n minus 1 instead of n for standard deviation. So that's what you have to figure out to actually use the chart. So let me make sure, let's try to use this chart. Anybody still need that chart? I think at least one person. Garrett? Everybody else has the t-score stuff? So let's take a look at this thing. Awake. Yes.
If the number you're looking for isn't on the chart, are you rounding? Or rounding to the nearest whatever's in the middle?
We'll talk about it. So there's a problem on that sheet where the degrees of freedom ends up not being on here. You will almost always be more conservative. Always in statistics, if there's anything you're not sure about, you make it worse for yourself. You make the interval bigger. So for example, on this sheet, there's one where n is 3. Do you see it? No. There's one where n is 93. The third one. If n is 93, what is the degrees of freedom? 92. Is that on the chart? No. So you use 90. Even if it was a degrees of freedom 99, you would use 90. But in that case, if you use the 101, you're fine. Does that kind of make sense? So you want to be more conservative always. Don't mean politically, but in terms of kind of punishing yourself for not knowing something, right? So some of my colleagues don't understand why I still use the charts, and then some of you guys are like, who are those people? Let me take them. Oh crap. Poor little thing. I feel your pain. That is the best you could do, isn't it? What's wrong? Let me try to reboot him. Alright, I forgot where I was. Alright. So let me make a situation up while this guy remembers how to work. If I had a sample size of 39, and I didn't know sigma, but I knew S. Do I need to tell you that it's normally distributed? Why don't you need to know Why don't you need to be told that? Because n's greater than 30. Okay, I think we all know that by now. So how to use this chart? So I could not use this formula because I don't know sigma. I've got to use this one. So what's really funny to me is people have trouble about, it's not funny to me, I don't laugh at your inability to do something. But I want to point out, when do you use a t-score? The formula tells you shit. Now what's also true? What tells me I could do either one of these? What do I always have to check first? What we just talked about, right? It's got to be normal to do either one of these. But then, when do I use Z? Only when you know sigma. When do you have to use T? When you only know S. The formula tells you.
What was S again?
Yeah, what's S? Oh shit.
Standard deviation of the sample.
Of the sample. I love it.
Oh,
Wow, that
that's-
was freaky. You guys
And that's population. The
practice that. Yeah, this one's population. Remember, population in the early going was like Greek symbols.
Oh.
Yeah. So this whole thing came from not knowing mu. And then there's an adjustment if I also don't know sigma. Okay, how are we doing? I like it. No? Shit. So in this case, if I wanted to create, let's say, a 90% confidence interval, I'm allowed to do something because n greater than 30, it's normal enough. What is it that I have to use, though? I've got to use a t-score. In order to use that chart, I've got to know what the degrees of freedom are. What's the degrees of freedom? Yeah. 38? Is 38 on there? Yay! So there's 38 now, how the hell do you, what the shit does this all mean? All right. And I've been trying to get you ready for this also. When you create a confidence interval, how many tails does it make? 2. So you can look at this in one of two ways. If there's 90% inside, what's in both tails? How much is in 2 tails? 10%. Well, how much is in 1 tail? And they both are the same stupid column. So 10% in 2 tails, 5% in 1 tail. Either way you look at it, you can't go wrong. People find a way to go wrong, but still, shouldn't. So I know I'm going to use this column, and I know I'm going to stop at 38. Boop. So 1.686. So if it would have been a situation where I knew sigma, I would have used a very familiar sounding number. I would have used 1.645 for the z-score. To cover my ass for not knowing sigma, I make that a little bigger. I make it 1.686 to end up with making my interval a little bigger. I like it. Kick ass. I love the analogy, even though I hate eating fish, not because I'm all nice about it. If I liked fish, I'd eat the shit out of it, but I don't like fish. But still, this idea of if you're less certain about how much a fish swims away from its little house, you're going to make a bigger net to cover your ass for being less certain. It might go that far. Well, let's make our net bigger. Shit. So it's the same thing. There's something I'm not sure about. We make the net a little bigger. The interval gets a little wider. Okay, how are we doing? All right, let's do a full example. What do I mean by that? I mean, there. So let's say I take a sample of 81 people. I get the standard deviation of, well, yeah, I do need X bar. I get an average of 9.14. Standard deviation of 2.87.
Can you make us calculate the standard deviation of sample, or just give it to us as box?
There will be situations where you have to use 1 bar stats to calculate your own S. Is that what you're asking?
Yeah.
Yes,
Or
okay.
to calculate it by hand, you said you'll be allowed to use one more stats.
Yeah, I think I told you guys that past that first test, I would never make you do the x minus x bar squared. Remember doing those tables? Yeah. I'm not going to make you do that table
ever again. You're just going to get S from one of our stats in the calculator. Because we got other shit to do. Right? Bless you. So why am I allowed to do something? Why am I allowed to do something? Because you're the teacher, Jeff. No. Why is anybody allowed to do something with us?
Because it's normal.
There you go. Create a 98% confidence interval. Why is it normal? Because n is greater than 30. I like it. Bless you. So whenever you're asked to create a confidence interval, if it's for a mean, you have to figure out to use Z or T. If it's for a percentage, you just check NP hat, NQ hat. What happened? Let me see. We never use a T-score for percentages because with percentages, we calculate our own standard deviation on the spot. It's kind of like we always know it. That's why there's only 3 confidence interval formulas, not 4. P hat 1 only has Z in it. That's it. So let's see, I've got most of what I need, right? Yeah, there's Z. Yeah, they're weird letter. I've got X bar, I've got S, I've got N. How do I get T? T-score chart. What do I need to know to use the T-score chart? Degrees of freedom. What would the degrees of freedom be? Bless you. 80. Yep, 81 minus 1. N minus 1 always for the degrees of freedom. Sorry. Bless you. And I want to be 98% confident, so which column am I going to look at? First, second, third, fourth, fifth. Which one? Why the second one?
That has 2%.
Beautiful. So if there's 98% inside, there's 2% in both tails. Or 1% in one tail. Either way, I'm in this column. What do I get if I go all the way to the bottom of the column? What do I get? Z-score. That's why I will use the T-score chart sometimes to get a Z-score. This is like that baby chart blown up a little bit, right? If I stop, I get a T-score. If I go all the way down, I get a Z-score. So I'm going to stop at, of course, 80. Shoot. And get 2.374. So now I've got everything I need. I know the T is 2.374. That was the last thing I didn't have for the formula. Now I can just throw everything in. Get this interval.
And why wouldn't you use 100 degrees of freedom?
Say again?
Why wouldn't you? Oh, never mind.
Because there's only 81, yeah. Poor little dude.
I thought it was 98 for a second.
Oh, I got you. Oh, yeah, 90% couple. All right, so now I've got 9.14, give or take, 2.374 of these. I think the error is going to be 0.713. That'd be really cool. I think it's kind of like, yeah. What is it?
0.757.
Oh, okay. Well, shit. That's not what it is. I'm upset at myself. Is everybody semi with me? So you get the error, so you know what to add and subtract from this dude. So what do I get for my little interval? Uh, 8.383? Yes? And then 9.897. Now, unfortunately for you, you don't just circle that and keep going. Because that's maybe like a third of the problem in a stats problem, really. You have to explain what the hell we just did. And you do that with that little statement at the end. The next chapter is going to have its own little statement at the end, just so you continue to have something to look forward to. So it says, we are what?
We are young.
What is it? 98% confident. About what? About anything, Jeff. Shit. We are 98% confident that the interval I didn't give any units for this, so, 8.383 to 9.897 contains the true mean. I wasn't feeling creative, so I didn't give any units or even any backstory, so too bad. But in general, if this was, what would this be, Jeff? I don't know. Number of months until a baby's born? Sure. Right, so roughly done. If that was what that was, then you would have to include that many months to that many months contains your true mean number of months until a baby is born. Okay, maybe I like it. All right. So, where did I put that? Oh. Here we go. This we sort of did something with this earlier this semester, but I love it, Jeff. That'll work. Okay. What I want to do, let's see. Yes.
For the formula for the degrees of freedom, is it just n-1?
Yep, just n-1. Yeah. Normally I have twice as many people, so what I want to do is I normally group people up into two, but you're going to be individual to start with. And the men are going to get the males' average grades up to this point in the semester, and the females are going to get the women's average grades. So, I want you to work on this by yourself first. I'm sorry, Brian. Okay. Apologize for playing nobody the wrong one. If anybody needs to borrow a calculator,